Advanced Math, Lesson 5. Exponents, radicals, complex numbers, areas of similar geometric figures, and diagonals of rectangular solids. We're going to focus on exponents, radicals, similar geometric figures, and diagonals. Complex numbers we can go over in class. They shouldn't be too difficult. They should be something you already learned in Algebra 2. So we'll be starting with example 5.1 right here. Why is everything... There we go. Example 5.1. We need to simplify this radical expression. So we'll go to our work paper. And we see we have the square root of x cubed y times the fourth root of xy cubed. So what we do here is we think of a root as being like a fractional exponent. So the square root would be like the 1/2. So x cubed y is being multiplied by an exponent of 1/2 because the square root is looking for pairs, or it would have the invisible number 2 here. Now for this number over here, it would actually be the fourth root, so it would be xy cubed times 1/4. So the way these fractional exponents work is whatever number is in this little hook of the radical, visible or invisible, is going to be the denominator of your fractional exponent. So in this case, since the invisible 2 cannot be seen, that's going to be to the exponent of 1/2, and since we do see the 4, that's the exponent of 1/4. Here we just simply distribute our exponent to give us x to the 3/2, y to the 1/2, and then x to the 1/4, y to the 3/4. From here, all we have to do is add like terms, or multiply the y's times the y's and the x times the x's. Remember, if you multiply numbers of the same base with different exponents, you have to add the exponents. So x to the 3/2, or well, 3/2 plus 1/4. That's what we're doing here. And then over here we'll be doing 1/2 for y plus 3/4. We're going to need a common denominator, so we'll convert this 3/2 to 6/4. We add it, and then we get x to the 7/4. Here this becomes 2/4 when we give it the common denominator, and that becomes y to the 5/4. And that's our final answer. So that's pretty simple. When you see these, just think of fractional exponents, and then this square root is going to apply to the whole number, so you kind of put it in parentheses and distribute. Now let's go to 5.2. This one's a little more complex. We've got much more going on. We have a to the power of x over 2 times y to the power of 2 minus x. This whole polynomial is one exponent being multiplied to the power of 1/2 over a to the 3x, y to the negative 2x. First thing we're going to do to simplify this is we're going to get it out of fraction form. So we're going to move this one and this one to the numerator, which is going to change their sign. So that rewrites the problem as a to the exponent of x over 2 times a to the exponent of negative 3x. Then we have y to the positive 2x, so I've eliminated that one, and that one. This one, before I write it, I'm going to go ahead and distribute it to save myself some time. 1/2 times 2 is going to give me y to the exponent of 1 minus 1/2 x. Excuse me. And the last thing we're going to do is we're just going to combine like terms by adding exponents. So we'll combine the a into 1, but first we have to add x over 2 plus negative 3x, and that's over 1. And then to add these fractions, we have to give them common denominators, so this would become negative 6x over 2. And then x minus 6x would give us negative 5x. So this would be a to the negative 5x over 2. Now for y, we have 2x plus 1 minus 1/2 x, or we can take 1/2 x and rewrite it as negative x over 2. That would be more suitable since we have to deal with this as a fraction. So we'll make it minus x over 2. We'll put each of these over 1, and then we have to get a common denominator. So this would become 4x over 2 plus 2 over 2 minus x over 2. So from here we see that the 4x and the negative x will combine, and that just becomes 3x. So what we have is 2 plus 3x all over 2. So that's going to be the exponent for the y. So our final answer will be a, negative 5x over 2, times y, 2 plus 3x over 2. Moving on. So we go to 5.8. We're going to go to the book for the question here. On 5.8, they tell us that the scale factor between two rectangles is 4. What is the ratio of areas? So I've drawn this out for you because all they're going to give you is the words. They're not going to show you anything. But if you remember that the scale factor is 4, that means the smaller triangle, or the smaller rectangle, this length times 4 would equal this length. So I can write 1 times the length is going to be the length of this triangle, or this rectangle, and for this rectangle we take 4 times that length, and that would be that length. Same thing with the width. So I've kind of drawn a scaled version of the problem. Now to figure out the ratio of the areas, let's just find the area of these two rectangles. 1 times 1 will give me an area of 1 units squared. Here 4 times 4 would give me an area of 16 units squared. So we can see the ratio of side to side is 1 to 4, and the ratio of area to area is 1 to 16. So that would be my answer. 1 to 16 is the ratio of areas. And what you'll notice is that in similar polygons, that will always be true. The ratio of side to side will be the same as the ratio of area to area squared. Or I'm sorry, would be the ratio of one side to the area squared, or side squared. So to do this without the drawing, if I had the ratio of, we'll use another example, let's say that the sides are in ratio of 1 to 3, well then I know right off the bat that the area would be in ratio of 1 to 9, because all I have to do is square the sides to get the area. And likewise, let's say we had sides in ratio of 2 to 5. The ratio of the areas would be 4 to 25. Is that making sense? Hopefully. All right, now let's move on to the very last problem, 5.11. Position my book here. So we have to find the length of diagonal AC, which is the top corner to the bottom left corner, the other side, of this rectangular solid. They want us to do two-step development. So we'll go ahead and just go straight into what a two-step development is. So again, I've expertly reconstructed this drawing on my paper. Never mind the wobbly lines or the crummy corners. Okay, so we have to find the length of this diagonal from A all the way down to C. To do that, first we can see that this would make a right triangle from A to C, from C to B, and then B to A. Now B to A is very simple, that length is M. However, B to C, we don't have a value for that length. We can find it if we use this rectangle to get the diagonal. So if we look at the base like this is the base here, one side is 2, one side is 3, we need to find the length of this diagonal. We'll just use Pythagorean theorem. So if we have a height of 3 and a base of 2, then we would do 3 squared plus 2 squared equals this length squared. We'll call it C squared. Would equal C squared. So from there we have 9 plus 4 equals C squared. We get 13, and the square root of C ends up becoming the square root of 13. So now we know our diagonal, our floor diagonal length. This floor diagonal length is going to be root 13. And that's going to be one of the legs of this diagonal we're working with now. And the other leg is going to be n, so we can use another right triangle. This right triangle will have a leg of root 13, a leg of m, and the diagonal here is going to be the diagonal we're looking for, A to C. So we'll just use Pythagorean theorem again. We do root 13 squared plus m squared equals AC squared, which is what we're looking for, this length. Let's work that out. 13 square root of 13 squared is just going to be 13 plus m squared equals AC squared. Take the root of each side, left with AC on the right, and then on the left we have to figure out square root of 13 plus m squared, right? Not really. That's pretty much how we can write it, because there's no other way to simplify this. There's no square root of 13. We can't find the square root of this polynomial, so our final answer is root 13 plus m squared. That's the length of the diagonal.